then we will start the new chapter. Okay. Regarding subthreshold conduction, this is one of the very important aspect of short channel effect. So the in subthreshold conduction, by subthreshold we mean is we know that VGS is if we plot IDS over VGS, okay, then it looks like this, where this is your VTH. So when VGS less than VTH, so we are discussing subthreshold conduction. Okay, by subthreshold conduction we mean is if we have so when VGS less than VTH, the current in the conventional sense we say it is zero, because the charge in the channel this is equal to 0 when VGS equal to VTH, right? But to be honest, the current I mean the carrier or the minority carrier is not equal to 0. So if we have a p-type substrate, okay, and so this is my gate, source and drain. Say if this p-type substrate is concentration is say of the order of 10 to the power 15 per centimeter cube, okay, then the minority carrier concentration will be of the order of 10 to the power 5, right? So to be honest, the minority carrier concentration in the substrate is not 0. So in this region there will be current. That current might be very low depending on a factor which is known as subthreshold slope. Okay, so that is what we have discussed in the last class. Now this subthreshold conduction depends on this particular factor, that is what is the minority carrier concentration in the substrate. Okay, and we can find out this subthreshold current because this is essentially a diffusion current because the voltage we are applying at the drain side between drain and source will be say low, and so the field in the channel region is very small, and also so this compared to drift current which we get in the when the MOSFET is on, compared to that it is very low. Okay, so drift current is hardly there is any, but there will be diffusion current if we have carrier concentration at the drain side and carrier concentration at the source side, there is concentration gradient, then there will be diffusion current. And we mentioned that this diffusion current we can calculate. Okay, and this is sorry, this is QDN minus QDN dN over dx, right? And this dN is diffusivity and dN over dx is the concentration gradient of this magnetic carrier, that is in this particular case is electron, and we can basically find out dn over dx by finding the carrier concentration at the source, carrier concentration at the drain divided by L, that is the channel length. Okay, now what is the carrier concentration at the source side? Carrier concentration at the source side, we can write it is this psi s is nothing but the surface potential. Okay, and carrier concentration at the drain side similarly can be written as or you can write VDS over KT, right? So this is the carrier concentration at the drain side. So if we use this, so we can find out J diffusion, that is the current density. Okay, and we know that dn can be written as from Einstein equation, dn over mu n is equal to kt over q, right? So we can use this expression and right. So this is another thing is this VDS. If VDS is more than KT over Q, okay, in the last class we considered VDS is say around 100 millivolt, then what will happen, this will be exponential minus 4, right? Because KT over Q at room temperature is around 26 millivolt, right? So you see, this term can be neglected and we will end up with J diffusion is equal to and it is possible to show psi s is proportional to Vg. In fact, if you remember to find out how to find out the threshold voltage of a MOSFET, this is the equation from where we find out the threshold voltage, right, of the MOSFET, and we similarly where this CD is basically depletion capacitance and COX is gate oxide capacitance. Okay, so D psi s and we in the last class we considered this as m. Okay, this factor as m, so dVd by m. So what we uh, can do from here, we can find out the current or expression of current. Just let me skip some of the steps, and we can write current when at the subthreshold region as this. Okay, so this is the drain current, and you see this drain current. So this K dash contains all the factors which are here. Okay, so so this K dash is constant, and you see this IDS is exponentially dependence on gate voltage. So we can take log at both the sides. Okay, so if we take the, if we do the differentiation with respect to Vg, so the way we define subthreshold slope is so subthreshold slope is inverse of this. So the unit is millivolt per decade. Okay. Uh, so if you look carefully, this is nothing but KT over Q M ln 10. So KT over Q is 26 millivolt and ln 10 is around 2.3. Okay, multiplied by M. So this is nothing but around 60 M. Okay, or 61 plus CD over Cox. Right. So this is at this millivolt per decade. That means if it is 60 millivolt per decade, so 1 order magnitude of reduction of current can be expected if you reduce 60 millivolt. So if I plot log IDS versus VGS, then so this slope is subthreshold slope, and if the base value we can have is 60 millivolt per decade, because this is, you see, KT over Q ln 10. So this is giving us 60, right? So this is the base value we can get. Okay, if we have like CD over Cox, this factor is negligible, but this factor we can't neglect it. Okay, so this subthreshold slope will be at least 60. So what does that mean is if you reduce 60 millivolt, okay, your current will decrease by 1 order magnitude, right? Say this is my threshold voltage VTH, okay, and of course after beyond VTH the current will increase. I mean, you remember it will go initially at linear region, then in the saturation region. Okay, so current will change more probably from probably maybe few milliamps, right? So that is is like very little change in the log scale, right? So this is my subthreshold slope. This represents couple of things. One is current beyond or below this threshold is not zero. This also represents that this subthreshold slope is um, below 60 millivolt per decade is not possible to achieve. Okay, often we get 80 millivolt, 90 millivolt per decade. Now the thing is, like, if we reduce the, so it doesn't change with node. So this SS subthreshold slope is independent of node. So if we go from 330 nanometer process to 180 nanometer process, okay, the subthreshold slope will not change. But you remember that as we move to future generation or future generation node, we need to reduce threshold voltage. You remember? So as we reduce threshold voltage, maybe say in another node the threshold voltage is here. Okay, say this is VTH2. Now you see the subthreshold, because of this subthreshold slope, this was I of, okay, now it is new I of is here, say I of 2. Okay, so you see the leakage current or the off current is much larger compared to as we move to the future nodes. Okay, in the long channel MOSFET the leakage current is much lower, simply because the threshold voltage is higher. Okay, but now in the short channel MOSFET the threshold voltage is lower, so the I of is much higher. Okay, what is the consequence? Consequence is you see that we have so far we in case of CMOS we only concentrate on power dissipation during the transition, right? In case of CMOS, we only concentrate on power dissipation in the during CMOS. So say this is my higher nodes, okay, and this is my lower nodes. So what will happen in higher nodes? Maximum power you're concerned with, say here, okay, and this power is mainly because of transition. Okay, dynamic power, and static power was very low compared to dynamic power, right? Now in the lower node, this static power is increasing, simply because uh, as we just now discussed, because of this similar subthreshold slope, the I of is much larger in the lower nodes. Okay, so now this subthreshold, because of this subthreshold leakage current, the power dissipation, static power dissipation, becomes comparable to that of the dynamic power dissipation. Okay, so what are the remedies? There are some remedies which we mentioned in the last class. um, the remedies are, if you look uh, if you look S carefully, that is 61 plus CD over COX, right? So if we increase, one of the remedies, if we increase COX, okay, then this factor will be negligible, right? And this will also help in getting higher IDS, higher GM, and so on. Okay, so this factor will be reduced if we manage to increase COX. That is one part. So that will improve your subthreshold slope. One can also use multiple VTH. This particular point we have discussed in the last class. What this multiple VTH will do? Say I have several million transistor in my chip. So what I can do is I can use some of those transistors at we can fabricate those transistors in such a way that some of them are higher VTH and some of them will have lower VTH. Now what higher VTH will do, so higher VTH FETs and lower VTH FETs. So higher VTH FETs will have low speed, low ion, right? Because VTH is high, right? Ion depends on VGS minus VTH. So if VTH is high, you'll have low speed, low ion, okay, from the FET. And but the most important is low static power dissipation, because high VTH means, you remember, the I of will be low, right? What about lower VTH? Lower VTH is FETs will have more speed, okay, higher ion, but high static power dissipation. So instead of having all the MOSFETs as lower VTH, we can use a combination so that we can get both the advantages, right? So this is another thing people tried. There are other things also. For example, you can reduce CD. How do you reduce CD? There are different ways to reduce CD. One is you can increase substrate doping, okay, because CD is, you remember, CD is what? So this is my oxide, okay, and there is channel and there is this depletion region, right? This depletion region gives rise to CD, right? So if you increase your substrate doping, okay, you will be able to reduce the CD. What about any other means? You can also use SOI to reduce your CD, okay, and so on and so forth. Sorry, I made a mistake. So not increasing substrate doping, decreasing substrate doping, right? So if you decrease your substrate doping, this depletion region will increase, that will reduce your CD. Or you can use SOI. If you use SOI, you remember, then there will be so N plus, and there will be oxide layer here, thick oxide layer. So if this part is fully depleted, then you see then there is silicon. So your effective dielectric layer thickness will increase, and that will reduce the CD. Okay, so this is what I tried to discuss in the last class, but I hurriedly did it because we didn't have time. Do you have any question regarding this? Do you have any doubt? You have any doubt regarding this? No doubt?
Hello, sir.
Yeah, please.
So can you please tell what are the factors in influencing K dash?
Then I have to go through that steps. So you check. I think you because we have spent so much time on this already. So you check. So this is J diffusion. Okay, J diffusion, and this psi S you can, if you look at the conventional semiconductor device book, you can you will get this formula. Okay, so that is the relation between psi s and Vg. This is VFB is the flat band voltage. You remember? Flat band voltage. And like at flat band, so there are different conditions. You remember at flat band, psi s equal to 0, but when psi s equal to psi b, you see then n not equal to ni. When psi s equal to 2 psi b, okay, uh, then you see it becomes n type. Okay, the way we define threshold voltage and all that, psi is equal to 2 psi b or 2 phi b, then this p type substrate becomes n type, right? So that way we define these are different different consequences of this formula, and we can find out dvg over d psi s. Okay, and it is possible to show this will give you 1 plus cd. Here also I have jumped some steps. It will give you 1 plus cd over cox. So you can find out relation between d psi and dvg this way. Okay, and you use this. So what we have done, like this is a factor which we defined as m, and what we can do is, like, from this J diffusion we can find out a corresponding current density, corresponding current, because that is nothing but J diffusion means means current density, and that is current. So all you have to do, you have to find out the, say this is the thickness of the layer, and this is my L, this is my W, through which the current is flowing. So you have to multiply this, okay, with J diffusion to find out IDS. So IDS uh, will have these factors, uh, because if you see IDS I have written Q, Vg, Vth, K, Tm and K dash. So you go through by yourself and see what you get for idea K dash. Okay, so K dash is a constant. If you want me to do, then I will upload this particular steps in the note in MS Team. Okay, is that will do? Okay, so this K dash will have the factors associated with this charge thickness and charge length and this charge width. Okay, because all you are doing, you are basically multiplying the area with J diffusion to find out IDS. Is that okay? Or if you want, I can calculate those steps and upload this whatever I have written here, because I have jumped some of the steps between J diffusion and IDS.
So if K dash is a constant,
Right.
it just depends upon the dimensions, right? So if you are having more slope, the IF would be smaller, right?
Sorry, say again.
So if K dash is a constant, if you're having
Right.
higher slope, IF would be smaller, right?
No, but you see, what we are doing, we are basically finding out. We are basically finding out dIDS over dVg. Okay, and this factor doesn't on dVg, doesn't depends on dVg. So that is why I am just neglecting this factor in this calculation. Is that what you are asking?
No, sir. But because if you're increasing cox, we are actually reducing the slope, right? But if I were to increase the slope, I would get much lower I of currents because K dash is a constant value.
Yeah, but K dash doesn't contain this COX. COX contains by this factor M, which I didn't neglect.
So I meant the 60 plus 1 plus CD plus C by COX factor.
Yeah, so 60 plus 1 plus CD over COX. Okay, this is S, and the minimum value of S we can get is 60. Okay, so what I wanted to point out is this 60 we can get, or close to 60 we can get, if we reduce CD and increase COX. Right? So the
Yes.
way we increase COX is if we reduce the thickness of the oxide, right? And the way we reduce CD, the way we increase COX is if we reduce the TOX. The way we reduce CD, if we increase the depletion width under the channel. Is that okay?
Yes, sir. Thank you.
Right. So now the thing is, next part what we are going to discuss uh, is we are now going to discuss some of the advanced uh, um, devices. Okay, one of them is FinFET. Okay, so one of them is FinFET. So let's start with this particular device discussion. The reason we want to discuss this particular device simply because nowadays in lower node we no longer have planar MOSFET. So whatever we have discussed so far is, you remember, this is a planar technology. So we have our source and drain and our channel all are in the same plane, right? And of course on top of that there is gate oxide and gate. So this is our planar technology based MOSFET, which is conventional MOSFET, right? Now in case of FinFET, it's no longer a planar technology. And in lower nodes means like 22 nanometer onwards, 22 nanometer onwards gate length, foundries starting or started developing different kinds of FET, which is known as FinFET. Okay. Specifically Intel in their 22 nanometer process started using FinFET. Other foundry, for example TSMC, they started FinFET around 14 nanometer process, and so on, right? So how this conventional FET in newer technology looks like. So FinFET is a kind of 3D device. Okay, Now, so this Finfet, uh, let me try to draw this. My drawing is horrible, but let me try, uh, so that you get a better picture how it looks like. So this is my silicon, okay. Right. How to draw? Uh, this is my silicon, and say this is my oxide, okay. Uh, Please don't draw after I finish drawing, then you will draw, okay. So uh, just almost done. uh, so say this is my source, this is my drain, okay, and this is my gate. Of course, this is the oxide layer. This is the oxide layer. So this is FinFET device. You see this particular portion, which is like a protrusion kind of structure, is a fin like structure, so that is why it is called FinFET, okay. So there is a source, there is a drain, and this is the gate which is wrapping the fin, okay. You see, gate is wrapping the fin. Now, before discussing more about FinFET, let's understand the motivation. Why do we need this kind of a 3D device? Because it's more complicated. We'll discuss the fabrication steps briefly of FinFET structure, and it's a very complicated kind of device to fabricate compared to planar FET. Okay, so why do we need such a complicated device? What is the motivation? So the motivation part, you see, we have already discussed, but let me reiterate once more, which we have just now mentioned. So motivation behind moving from planar technology um, to this uh, 3D kind of technology is simply because of short channel effect. Okay. simply because of short channel effect. Now, so two short channel effects play important role for the development of FinFET. One was subthreshold slope, okay, and the another one is Dibble. Both of them we have discussed already, right? Now, you remember we said like say in one node this is my VTH, and in lower node, because we are decreasing VTH but the subthreshold slope will remain the same, okay, so we'll have much higher I off, right? This is we just now discussed. Now the thing is, in short channel effect, this I off becomes all the more problematic. Why? Because you see, along with this subthreshold slope or subthreshold conduction, there will be dibble. So this dibble of a MOSFET, what it does, it will reduce the, it will reduce the threshold voltage, right? So from the same MOSFET, because of the dibble, there will be reduction in threshold voltage. Now you see, because of this reduction in threshold voltage, the I off will increase. So one is you are reducing the node. So this is node say 45 nanometer process, okay, and say this is 22 nanometer process. So as we have reduced the node or gate length, we have also reduced the threshold voltage. That is one point. Another point is, if we reduce the node for the same node, say 22 nanometer process, because of dibble, the threshold voltage will decrease even further. So I have, this is my 22 nanometer process, VTH, but because of the dibble, what dibble will do? Dibble will, you remember, so this is my band diagram. So if we increase VDS, then this slope is going to decrease, right? So without the effect from VGS, without effective performance of VGS, still we will be able to reduce the barrier height, and that will allow electron to reach from source to drain, right? So this effect is known as dibble. This, in another words, this will reduce the threshold voltage, right? Effective threshold voltage is going to decrease. Now this effective threshold voltage, when it going to decrease, that will effectively increase the I off, okay, right? So for the same node, you don't have to reduce the node. If it is a short channel MOSFET, for the same node, okay, we will have reduction in threshold voltage because of dibble. And what this reduction in threshold voltage will do, this will increase the I off, okay. Now, so that is a very problematic factor in short channel MOSFET, because in the short channel MOSFET we have lower threshold voltage, because we are reducing the dimension, and we have to reduce the threshold voltage, as we already discussed several times. But additional reduction in threshold voltage comes because of the dibble, right? Now, what we can do to improve the situation? We can, if we have better control from the gate side, okay, we can reduce the effect of dribble, you see, if we have better control from the gate side, right? And we can improve the subthreshold slope. Now, one way to understand this analogy in a better manner is, say I have two bucket of electron, okay, so I have one bucket of electron which is known as source, one bucket of electron which is known as drain, right? And I have gate here, right? So water here, maybe water here, water is flowing through this pipe. Now this gate is kind of a lock to control this water flow through the pipe, okay? Now there are few things we can do to improve this control, okay? So if we reduce the distance between the source and drain, that is, if we so there is a, you see, this is like potential well kind of structure, okay, or maybe bucket of water, you can think that way as well. So if we bring source and drain very close, this gate find it very difficult to control water or control flow of electron from source to drain if they are very close, okay. So one thing we can do, we can use multiple lock. So one is we can use multiple lock so that we can control the flow of this water or flow of this electron. Another thing we can do, we can narrow down this pipe. If we narrow down the pipe, that will also reduce the water flow, you see. So this is basically the motivation behind FinFET. Okay, so if we say we want to have like multiple lock or say multiple gate, so we can have gate at the top, we can have gate at the bottom, we can have gate at the side walls also, we can have gate all around also of the pipe to improve the control. Okay, now so that is how we can have like double gate structure, tri gate structure, gate all around the structure. So let me draw a couple of the cartoons very quickly, okay, just to show you how we are getting more and more gate control over channel, okay, more and more control from gate side over channel. So our bulk silicon in the planar technology, right? We have oxide and we have gate. This is our planar technology, right? Planar device. Then we have discussed SOI. In SOI we have handle silicon we have box, that is buried oxide layer. Then we have active silicon layer, okay, or silicon on insulator SY. Then we have oxide again. So this is box, this is oxide layer, and this is gate. So this is also planar device. But you see in SOI, this wafer, this silicon on insulator layer or active silicon layer is very, very thin. That is like we are reducing the or narrow down the pipe. Okay. So it is even thinner if you use FD-SOI, that is fully depleted SOI. We haven't discussed fully depleted and partially depleted SOI, but just let me mention that if it is fully depleted SOI, the thickness of this active silicon layer is much thinner, and we can have like we can have like more control from gate side. Okay. Then there is further improvement. We can use double gate structure. So we can have like silicon, there is one gate here, gate 2, okay, channel and oxide, and there may be gate 1 here, okay. So this is like the double gate device. So as we are going towards right or going towards arrow, we are having more and more control. Okay, this is like double gate structure. I mean, double gate structure might be of similar thing, like probably you have heard like top gate and bottom gate type FET. Okay, so that's essentially a double gate structure. Now this double gate structure we can rotate. Say if we rotate it or flip it by 90 degree, we will get a kind of fin-like structure. How? So if we rotate this by 90 degree, you see we will have this is my silicon oxide. So this is my fin, okay. And so basically we have rotated it 90 degrees, say. And this is my gate, okay. So this is my gate and this is my fin. This is known as Finfet. Effectively in Finfet there can be two gate structure, okay. One is this is my gate 1, this is my gate 2, okay. And in the top portion there is usually thick. So this is my silicon. This is my silicon fin, okay, that I have drawn at the beginning. I've drawn at the beginning, right? And I am basically what I am looking at. I am basically looking cross section along this plane. So I will see fin and the gate, right? So I'm looking at cross section in that plane. So I'm seeing so fin, then gate 1, gate 2, and this is maybe thick oxide or nitride layer. So this is essentially a double gate structure, okay. Two side gates, but top gate I am not using because it is very much thicker, okay, thicker insulating layer. But in the side the insulating layer is very tiny, so that we can have two gates, okay. Now we can have like 3 gate structure also, where so this is my tri gate structure, In the tri-gate structure, we will have this protrusion or fin, and oxide all around it is thin. Okay, so we have gate here, gate here, gate here. So tri-gate structure, right? More control compared to Finfet. We can increase this gate little bit further. Okay, so what I mean is this is my fin, okay, and I am increasing gate little bit lower than that of fin. Okay, this is, we call it pi gate structure. We can get more control if we have like gate like, so this is my fin. If we have gate structure like this, okay, which is known as omega gate structure, okay, and we can have ultimate control from gate side if we have like my fin and gate all around it. Okay, so this is known as gate all around structure, and so on. So this is, you see, stepwise different control from gate side, but things will be, as you understand, things will be more and more complicated, right? The device is no longer a planar structure, it becomes almost 3D. Okay, but you will have better gate control if you have these structures. So we will be able to manage the subthreshold slope, okay, if we have more gate control compared to planar FET. So that will reduce the leakage current. So that's uh, the motivation. Now let me go through briefly some of the challenges associated with FinFET. Okay, so you see, process challenges. Okay, now here you see gate is vertical, you see your source and drain is vertical, right? So whatever material you are depositing, for example gate oxide around that gate region, for example metal contacts at source and drain, all this has to be like conformal. So conformal deposition is important. Okay, which is not easy. Conformal deposition of dielectric and metal layer. Dielectric and metal layer. Because as I said, we have this is my fin, okay, my source and drain. So we need sorry, we have to deposit, you see, metal contacts around source and drain, right? That has to be conformal. Now we have to have like a dielectric layer here. So this dielectric layer also has to be conformal. It should uniformly deposited on this 3D fin, right? So it is not easy, this conformal deposition of dielectric layer and your metal layer at source and drain and at the gate side, right? Now I would like to mention three challenges associated with fin structure. One of the challenges known as corner effect. What is corner effect? You see, unlike planar technology, in this is my fin, right? Now this fin, through this fin channel will be formed. Okay. Now these fins has these corners. So if I apply a voltage, although the voltage will be uniform, okay, at a particular portion of the particular position of the fin, but because of this corner, the electric field near these corners will be higher compared to these edges. Okay, so electric field at corners will be higher compared to edges here. Okay, so the potential is uniform, but at the corner electric fields are higher compared to that of these edges. You see, now if the electric field is higher at the corners, that means there will be more number of electrons here, right? More number of electrons here. So population of electrons will be more at the corners than that of edges and here, right? Now if that happens, that means you will have multiple threshold voltage, right? So with lower threshold voltage, you will be able to form channel near that corners compared to that of that in this middle portion or at the side walls, right? So although we said like we managed to solve the problem or improve the situation through FinFET development as far as the threshold voltage is concerned, because you remember through Dibble, if we have different threshold voltages, the lower threshold voltage will give lots of more leakage current and all that. Now the thing is, the same problem exists here because of this corner effect. There are corners, the corners will have more electron for the same voltage, okay, compared to electrons at the edges of the fin, and these more electrons means effectively there will be multiple threshold voltages, right? So that will again give problem of to your subthreshold leakage current, right? So this is basically corner effect. So population of electrons at the corners compared to that at the edges, and those population of electrons at the corners will give rise to lower threshold voltages. So again you will end up with multiple threshold voltage that will give you higher leakage current. Okay. So multiple VT. Now how to improve or how to solve this problem? You can solve this problem by removing the corners, right? Because of the corners we have this problem. If we can remove the corners, then this problem will no longer be there. So you can okay. So what we can do, we can remove the corners. Okay. So we can have fin like this. Okay. So to get rid of corners, one thing you can do, you can remove the corners by anneal. Anneal means high temperature treatment. Anneal in hydrogen environment to round off those corners. Okay. You can taper the fin. So second approach is you can taper the fin. Tapered fin. Or you can use side gates, not the top gate. Okay, that we have briefly discussed already. So conventional Finfet, in conventional Finfet, so this is my silicon fin, this is silicon nitride, and then we have like thin uniform gate oxide, right? So here we are not using top gate, we are only using side gates, you see. So this is like double gate structure. Which is basically conventional Finfet. Okay, so we can use we can create fin, but in the top portion the insulating layer is much thicker, so we will not take the we will not take the we will not use the top gate, we will use only the side gates, right? So that way again you can solve the problem. Now the thing is, in case of rounding off the corners, okay, you will have multiple width of the fin. Say this is W1, this portion is W2, and so on. Here also in tapered fin the situation is all the more complicated. It is like the fin is gradually width is changing. Okay. Now the thing is, if you have this kind of rounding off of fin or tapered fin, you will have multiple silicon axis open up. Okay, if we have multiple silicon axis like 100, 110, 11, 111, and so on and so forth, we probably know some of these crystalline planes, right? You have heard about them. So if you round off these corners, or if you make it tapered, you will have like multiple crystalline axis will open up. So if there is multiple crystalline axis, you probably know that along different crystalline axis or crystalline plane, the mobility of the carrier differs. Okay, so you will end up with different carrier velocity at different parts of the fin, which is again bit problematic. Okay, so these structure 1 and structure 2, they're like off, they call it off axis plane or not regular crystal planes. Okay, and carrier transport will differ, right, which is not the case in case of DG structure. But of course then you can't use the top gate, right? You can use only two sides of the gate, right? So this is first process challenges. Now the second process challenge is spacer stringer. Okay, what is a spacer layer? Spacer layer is again very important for in conventional planar MOSFETs. Okay, I think you know about it, but just let me briefly tell you. So you have like gate oxide, you have like polysilicon. Okay, and what we do, you remember in planar technology we use lowly doped drain. Okay, lowly doped drain, you remember we talked about lowly doped drain to avoid or to reduce hot electron effect. Okay, in the lowly doped drain, there will be voltage drop across that lowly doped portion of the drain, and the electric field in the channel will reduce, and that will in effect reduce the hot electron effect. Now this lowly doped drain is, I mean, the special layer is required to create this lowly doped drain. Okay, because you have like, I can't remember properly, but you see we have like N minus region. You first form the N minus region. Okay, then you form a special layer. Special is silicon nitride, usually is made of silicon nitride. Okay, so this silicon nitride layer you will create, and then you need to create all over the substrate. Okay, then you etch silicon nitride from the horizontal part. So you need to etch silicon nitride from here, from here, from here. Okay, only this portion adjacent to the gate, this vertical portion will have silicon nitride adjacent to the gate, because the horizontal part you manage to selectively etch, but this vertical portion will remain. And then you do another implant which is N plus. So this is your N minus you have done, then do you do N plus. Okay, so you end up with N plus and N minus portion. Okay, and so on. So anyway, so this is my special layer in conventional MOSFET process. Special layer is very important and heavily used. You always use them, right? Now this special layer is very important, as I said, in planar technology. Now how do you realize this special layer for your FinFET? Okay, because in FinFET, I have to draw it again. Drawing is a problem. Um, okay, so this is my gate, and then this is my So this is my source, this is my drain, and this is my gate, right? Now what we have, like, if we want to realize our special layer, okay, you remember I mentioned, like, when you etch it from the horizontal part, this special or silicon nitride layer will be etched. So it will be etched from this top of the gate, it will be etched from the top of the source and top of the drain. But this vertical, near this vertical portion, this will remain intact. Okay. Now, when you create this special layer in this 3D kind of structure, okay, so there will be special layer not only around gate but also around drain and source. Why? Because drain and source, now they are also vertical. You see, drain and source, they are also vertical. So if I draw this special layer, which I'll find it very difficult to draw. Uh, so this is my, say, this is my special layer. You see, that is around the gate. Okay. What about here? Here also there will be special layer. Right? So this special layer now will be around, not only around gate, okay, also around source and drain, because the way you etch it, you etch the from the horizontal part. So special layer will not be there on top of here, on top of gate, on top of these fins. Special layer will not be there, because the way you etch it, but it is there on the side walls. Now it is good for planar structure because it is there in the side walls around gate, but it is here in, for Finfets, the side walls for drain and source are also vertical, so the special layer will be there. Now that is a problem. Why that is a problem? Because you see, your source and drain needs to be doped, right? So you need to open your source and drain so that you can implant there. So you have to remove your special layer at source and drain. Another point is, this special layer is made of silicon nitride, okay, usually. Now you need to open your source and drain so that you can have metal contacts. You need metal contacts here, right? You need metal contacts here and here. Now the thing is, if it is like special layer is there, you can't have the, you can't realize this metal contact. Now what you can do, uh, if you look carefully, this gate is, height of the gate, end of the day, height of the gate is more than height of source and drain, right? Height of the gate is more than source, height of source and drain. So if I take a cross section and look at the cross sectional view, uh, look at the cross sectional view, the, so this is my, so if I look at cross sectional view from the across the gate, this is the special layer, and around source and drain, this is the special layer. Source and drain height is lower than that of gate. So what I mean is, how to, how to explain. I'm drawing I'm drawing that special layer around gate here. So this is my gate, okay, and this is my source, and so this is gate, this is source or drain, okay. So source and drain height is lower than that of gate, right? So this is basically my edge gate, right? So, and this is nothing but H fin, say, okay. So what people started doing to solve that problem is further in situ etching. Primarily using deep reactive ion etching, DRI, okay. So how long you will etch it? You will etch it until you remove special layer. So these are my special layers, okay, until you remove a special layer around source and drain. So you end up with, so that we end up with um, this is my H fin. You remove the special layer around your fin, okay, but you have it uh, you have some special layer around gate oxide, and you have, as I said, you need to etch it uh, unless and until you remove the special layer around source and drain, okay. That will reduce the special layer around gate, but that has not, that will solve the problem, okay. But the thing is, you see, you need additional process steps, okay, to remove spacers from the fins, around the fins, okay. So these are additional process steps. Now I will take probably 5 more minutes. So another challenge is source and drain formation. Okay, so another challenge is source and drain formation. What is, so in Finfet structure, you see, I mean, in conventional structure, in conventional FET, you have like conventional FET. You implant source and drain here, right? And this is your xj, that is junction depth. And every process node, in newer node, you reduce xj, right? As you reduce xj, your resistance associated with source and drain will increase, and that will increase your resistance at the source and drain. So you see, you increase the doping concentration at source and drain. You remember, right? So every process node, you need to reduce junction depth, and you need to increase your doping concentration, so that you can manage your resistance associated with source and drain, and so on and so forth. Now this junction depth, you have to define junction depth differently in FinFET. In case of FinFET, junction depth is nothing but the thickness of the fin. Okay. Junction depth is nothing but the thickness of the T silicon, so thickness of the film. Okay. Now the thing is, all I want to point out is like here, here you implant only this part or this part. It is much easier, right? But here you have to implant in all over this film, because this entire portion is the junction. It's not like this part is the junction. That's not the case, because you see your gate is all around this. So your junction, this is entire part is basically your junction. Okay, your source, and the other part is your drain. So this entire part you have to implant or you have to dope. Now that is very challenging, because you have to dope from the top, you have to dope from the side walls. Okay, because if you try to implant from the top, maybe it will not go all the way down. So you have to dope from the side walls as well, which is not easy, because if you think carefully, say I have multiple fins, so I have fins here, here, here. So I have many fins because I have millions of MOSFET, right? Say this fin and this fin is N type, okay, and say these are P type fins. So what I have to do, I have to put resist here so that I can cover these fins which I don't want to do. So say this is N type and these are P type. So I'm trying to dope these fins which are open. So say maybe these are P types. So if I try to dope it, we have to dope it vertically. Then also we have to dope it uh, in an inclined manner, and so on and so forth. So vertical is not an issue. When you try to dope it in an inclined manner, okay, then there are resist, and this will give some shadowing effect. Because it is difficult then to reach in the side walls, because there are resist here, right? So this is known as shadowing effect, and one way to get around that is known as uh, plasma doping. Plasma doping is less directional compared to that of conventional ion implantation approach. Okay, so people can use plasma doping, but this is another challenge, you see. So okay, so I will stop here today. Do you have any question whatever we have discussed so far? So I will upload FinFET notes, and also whatever I have scribbled, did board work, I will also upload this piece. But if you have any question, please tell me regarding any doubt regarding FinFET. No doubt. Okay, so in the FinFET so far, what I have discussed is the motivation behind FinFET, how the FinFET structure looks like, and very specific 3 challenges we have discussed. There are many other challenges to form FinFET. Okay, so we have discussed corner effect, we have discussed source drain formation, and we have discussed spacer layer problem. Yes, yes, Pavan.
Could you explain shadowing effect once more?
Yeah, this shadowing effect is basically, as I said, like there are many fins, right? So these fins, uh, so you have to cover some of the fins. If, for example, I have just said like these two are say I'm just assuming these two are say N-type fins. Okay, these side ones. Now what I have to do, I have to put resist here to cover these fins, and then I have to do ion implantation so that I can make these fins P type. Okay, maybe I have to dope it with boron and all that, right? Now once I try to do that, I have to, as I said, I have to access this sidewall also, right? So that I can dope them uniformly. but these side walls, access of this side wall is difficult because we have like resist coated from the sides, right? So all we have to do, so this is basically shadowing effect. Now I mean there are different ways to dope it. Instead of iron implantation, which is the conventional approach, we can use plasma doping approach, which is I mean I'm not going into the detail what is plasma doping and how it realizes and all that, but in plasma doping it is less directional, so you can get away with this shadowing effect and you can access those side walls. Okay.
Yes.
But this shadowing effect is coming because of this covering of with photoresist layer, okay, or resist layer, right?
Yes.
Okay. Okay. So we will meet tomorrow. Thank you very much.